Next, some formulas or definition. Average power of for random process. The average power of random process x of t is defined by pxx of t, which is equal to 1 by 2 pi integral minus infinite to plus infinite sxx of omega d omega. The average power over time interval minus t to plus t, that is time average, is given by limit t tends to infinite 1 by 2 t integral minus t to plus t expected value of x square of t dt, that is mean square or second moment. So pxx is the time average of the second moment. Now Wiener-Kirchhoff theorem. So we'll see the statement. Let x of t is a real WSS process with power density spectrum S xx of omega. Let x capital T of t be the portion of the process x of t in time interval minus t to plus t. That is x of t which is equal to x of t, small t lies between minus t to plus t, 0 otherwise. Xt of omega be the Fourier transform of xt of t. Let xt of omega be the Fourier transform of x capital T of small t. Xx of omega, which is equal to limit t tends to infinite 1 by 2 t expected value of modulus x of t of omega square. We'll see the proof. Given xt of omega is a Fourier transform of x of t of t. Therefore, x of t of omega, which is equal to integral minus infinite to plus infinite xt of t e power minus I omega t dt. So we are using Fourier transform formula. Xt of omega, which is equal to integral minus t to plus t xt e power minus I omega t dt. Because given xt of t, which is equal to x of t in the interval minus t to plus t, 0 otherwise. So we are taking the integral limit minus t to plus t. Now modulus of x t of omega the square, which is equal to xt of omega into xt star of omega. Star of omega is nothing but x of star, means conjugate of x. So xt of star omega is the complex conjugate of xt of omega. Now it is equal to integral minus t to plus t xt of e power minus I omega t dt into integral minus infinite to plus infinite x of t e power I omega t dt. By using one, we know xt of t, which is equal to x of t in the interval minus t to plus t, right? E power minus I omega tau. And second one minus t to plus t xt of e power I omega t, because we are taking the complex conjugate, right? So integral minus t to plus t x of t1 e power minus I omega t1 dt1 into integral minus t to plus t x t of t2 x of t2 e power I omega t2 d of t2, because we need separate variables to evaluate those integrals. That is why we are taking for the first integral t1, for the second integral t2, which is equal to. So we are taking the integrals together. So integral minus t2 plus t, integral minus t2 plus t xt1 xt2 e power minus I omega t1 e power I omega t2 dt1 dt2. So modulus xt of omega the square, which is equal to double integral minus t2 plus t xt1 xt2 e power I omega. We are taking I omega outside, which is common in e power. Then balance we are having t2 minus t1 dt1 dt2. This is equation number 2. Now changing the variables. We are using changing the variable techniques. Take t1 equal to t. So t2 minus t1 is equal to tau, right? We are taking t1 equal to t, t2 minus t1 equal to tau. Therefore t2 equal to tau plus t1, t1 equal to t, that is why tau plus t. So t2 is equal to t plus tau. Now dt1 dt2. So we are using the Jacobian transformation, right, for calculating dt1, dt2. Jacobian J, which is equal to dou t1 dou tt, dou t1 dou t tau, dou t2 dou t, dou t2 dou tau is equal to. So we are partially differentiate t1 with respect to t. So t1 equal to t. So when you are differentiating t1 with respect to t partially, so you will get 1. Now t1 with respect to tau. There is no tau term in t1, only t. So we will get 0. Now take t2. T2 is nothing but t plus tau. So integrating partially with respect to t. So you will get 1. Differentiate partially with respect to t. So you will get 1. Again differentiate t2 partially with respect to tau. You will get 1. Right. So we are having the determinant 1 0 1 1 2 by 2 determinant. So we are cross multiplying the main diagonal 1 into 1 and 1 into 0 minus 1 into 0. So we will get 1 minus 0 1. Now dt1 dt2, which is equal to modulus Jacobian into dt d tau. So modulus Jacobian 1 dt into d tau. So nothing but dt into d tau. Now to find the limits. When t1 equal to t, t is equal to t. When t1 equal to minus t, t is equal to minus t. Next limit. T2 is equal to t, tau which is equal to t minus t, because we know t2 is equal to tau plus t. Therefore we are taking here tau which is equal to t2 minus t, right? So t2 equal to t, so t minus t, and t2 is equal to minus t, tau is equal to minus t minus small t. So from 2, using the change of variable techniques, x capital T omega square, which is equal to minus t2 plus t, integral minus t minus small t, t minus small t, x of t plus tau, e power I omega tau dt d tau. We have changed every variables, right? Expected value of x of t omega whole square modulus value, right, which is equal to expected value. We are taking expectation both side. Expected value of integral minus t2 plus t, integral minus t to t minus t, x of t plus tau, e power I omega tau dt d tau. We are taking expectation inside the integral without loss in generality. So we will get, so double integral expected value of x of t plus tau, e power I omega tau dt d tau is equal to, we know expected value of x of t plus tau is nothing but autocorrelation Rx of tau. So double integral Rx of tau e power I omega tau dt d tau. So multiplying by 1 by 2t and taking limit t tends to infinite, right? So we will get limit t tends to infinite 1 by t, expected value of x of t omega square, which is equal to limit t tends to infinite 1 by 2t double integral Rx of tau e power I omega tau dt d tau. So which is equal to limit t tends to infinite 1 by t. So integral minus t small minus t upper limit capital T minus t r of tau e power I omega tau dt, integral minus t to plus t dt. We are separating the integral. Is equal to limit t tends to infinite 1 by 2t integral minus t minus t minus t r tau e power I omega t d tau. So integrating dt you will get small t, lower limit minus t, upper limit t. Substituting the limits t minus t, so you will get 2t. So already you are having 2t in the denominator, so 2t and 2t get cancelled. So we will get limit t tends to infinite integral minus t minus t minus t r tau e power I omega tau d tau, which is equal to, so this limit is for only t, capital T. So limit becomes minus infinite to plus infinite, right? Because t tends to infinite, lower limit becomes minus infinite, upper limit becomes plus infinite. Inside the integral there is no capital T, so r tau e power I omega tau d tau. That is nothing but s x of omega, Fourier transform of r of tau, correct? By definition of power spectral density. Hence limit t tends to infinite 1 by 2t, expected value of modulus x of t omega whole square is equal to x s xx omega. That's all. We'll see in the next video. Thanks.